Okay, so we've done one example of simulation, shown how we've taken, in that case there was 6 random variables, the sales amounts for 6 months, but they all had the same random distribution. That is, they were all normally distributed. They had a mean and a standard deviation. Before we do another example, I want to talk briefly about some of the other kinds of distribution functions we can use for our random variables, or so those things that we're uncertain about. We're going to talk about 5 different specific distributions. The last one is a little more advanced. I won't expect you necessarily to use it on an assignment, but it's somewhat easy to explain anyway, and it'll follow from some of the others. So let's talk about some of these different random variable distributions. So we talked about the normal distribution depicted here. So the normal distribution, and in this case we're going to kind of assume it was a mean of 1 and a mean of 0 and a standard deviation of 1. What that really means is, so the black curve here represents the normal distribution. Its highest point is at 0, or whatever mean you've chosen. Okay. What the standard deviation really says in the normal distribution is the values plus and minus standard deviation around the mean, so plus 1 standard deviation or minus 1 standard deviation away from the mean, you're 68% likely to get a value in that range. Okay, so for example, thinking back to those sales numbers, they were something like 1.8 million and the standard deviation was 80,000. So that means a mean of 1.8 million plus or minus 80,000 was 68% likely. It's 95% likely that you'll be somewhere plus or minus 2 standard deviations away from the mean. So 2 times the standard deviation above the mean or 2 times the standard deviation below the mean. That's a 95% likelihood. And it's something like 99%, 99 plus percent, likely that you're 3 standard deviations away from the mean. So basically beyond 3 times the standard deviation away from the mean is pretty statistically impossible, or very, very unlikely, okay, that you'll see values like that. In our simulation of 1,000 things, you may get 1 or a couple values outside of 3 standard deviations away from the mean. Okay, so that's just how unlikely they are. But that's the normal distribution. So it basically says you have one mean or expected value, and you have sort of a range governed by this standard deviation that says how likely or how far away from that expectation are you going to be. So you're 68% likely to be within 1 standard deviation away of the mean, 95% likely to be within 2 standard deviations of the mean, and so forth. Okay. There's more you can talk about the normal distribution mathematically, kind of how it was derived and so forth. We're not interested in that for this class. So this is just one of several distributions we can think about. On an assignment or final exam or anything like that, I would tell you if I want you to use the normal distribution in your simulation assignment or exercise. Okay, so I would just give you, the parameters to say, here's the mean, here's the standard deviation. Okay, in the real world, you may have to rely on experts to tell you something like that. You might have to rely on just some intuition, knowledge that would say this value is probably normally distributed. That is, I think there's a good chance it's some expected mean value plus or minus some standard deviation or plus or minus some range. It may be outside of that range, a little less likely. It may be 3 times, outside that range with very little likelihood. Okay, if you had a situation similar to that, the normal distribution is what you're looking at. All right, so that's one kind of distribution. Another very simple distribution is just the uniform distribution, which means you have a minimum value, here we'll call it A, and a maximum value B, and it's equally likely that it's any value in that range. That is, it might be the minimum, it might be the maximum, it could be halfway in between, 3/4 of the way in between, but every value is as equally likely as any other. Okay, it's impossible to be outside the range, that is, more than B or less than A. But within that range, every value is as likely as any other. Okay, so that's just a uniform distribution. Uniform in the sense that it's uniformly likely to get any value inside that range. Okay, so those are two basic distributions, the normal and the uniform. If you had something a little more complex than uniform, but maybe not quite as curved and complex as the normal, you can think about using something like a triangle distribution. Okay, a triangle distribution just says you have a minimum A value, you have a maximum B, but instead of being uniform, instead of every value being equally likely, basically there's a most likely value somewhere in between, and any value beyond that is less and less likely the closer you get to the extremes. That is, the closer you get to A or B, the less and less likely the value, the less and less likely it is that value. But there's some value in between. Maybe it's halfway in between, or maybe it's not. But look, on this chart we call it C. That's the most likely value. Okay, so there's sort of the expected most likely value and a range of possible values. But the further away from the expectation you get, the less likely we think that is. Okay. So where the triangle distribution is very sharp and pointy, the normal distribution is very soft and smooth. You know, you might have intuition of why to use one or the other in the real world. Again, on an assignment, I would just come right out and tell you, use this one or that one. Okay. The one nice thing about the triangle distribution is there is an absolute minimum and an absolute maximum value that it could ever take. Theoretically, the normal distribution, you could get a value more than 3 standard deviations away. It's just very, very unlikely, right? But theoretically, you could get a value 5 and 6 standard deviations away from the mean, okay, if you simulate it enough times, or maybe just got that unlucky. Okay, the triangle distribution, there's hard limits. There's a minimum, there's a maximum. You'll never go below the minimum or above the maximum. Okay, so that's kind of a little bit of maybe why you would think about choosing one or the other were you to choose. Okay, so normal, uniform, triangle distributions. Okay, pretty simple. On the final exam, I might ask you something like identifying these from these kinds of curves. So if I showed you charts that look like this, I might expect you to tell me which one of these is depicting the normal distribution, or which one of these is depicting the uniform distribution or the triangle distribution. Okay, just so that I know fair enough that you kind of understand what these distributions look like, what kind of values you can expect to get out of them. Okay, so those are 3. 2 other distributions that come up and are useful in some kinds of problems, but are very simple. One is called the Bernoulli distribution, and it looks like this. The Bernoulli distribution just says there's only 2 possible values. For simplicity's sake, we'll call them 0 and 1. And one of them is P likely, that is, with probability P, you'll get that value. The other one is just 1 minus P, that is, the other percent of the time you'll get the other value. For example, if you're going to flip a coin, the likelihood that you'll get a head or a tail, right? Those are the only 2 outcomes. There's no other outcome yet, unless you somehow manage to balance the coin on its side, right? You can't see the head or the tail. Right, you're going to get a head or you're going to get a tail. There's only 2 outcomes. In that case, we would expect it's equally likely to get one or the other. Okay, there might be cases where you have the choice between 2 things, and one is a little more likely than the other. Okay, either way, it's a Bernoulli distribution. It's 2 outcomes only. There's a probability for one, and the other one is defined as just 1 minus that probability. That is, it's the other percent of the time. Okay. Now, if you took a Bernoulli distribution, say you flipped a coin, you wanted to say it's 50% likely I get a head, 50% likely I get a tail. What if you took that experiment, flipping that coin, and did it 10 times. Okay? Then you could ask the question of, what's the likelihood of 10 heads, or 9 heads, or 8 heads, or 7 or 6, or so forth, right? So multiple Bernoulli distributions, basically stacked together. That is, what's the likelihood that I did a Bernoulli equation or a Bernoulli experiment over and over again? How many times would I see 0, or how many times would I see 1? Okay, that is called the binomial distribution. Okay, and I have a somewhat complex chart here depicting that. So the binomial distribution is the likelihood of any given value taken from a repeated Bernoulli distribution. That is, again, flipping a coin. If I flipped a coin 10 times, there's basically 10 outcomes, right? I could get 10 heads and 0 tails. I could get a head 1 time and a tails 9 times. I can get a head 2 times and 8 tails. I can get 3 heads and 7 tails, and so forth. But there's different likelihoods of each of those, right? If I'm flipping a coin, probably you would expect that I'd get 5 heads and 5 tails. Since it's equally likely I'd get one or the other, I'd expect to get about half of the heads and half tails. But it's somewhat likely that maybe one of those times I got an extra head or an extra tails, right? Or so forth. So the binomial distribution, if you think about that, basically has 2 parameters. It's the number of times you repeat the experiment, the number of coin flips you do, and the probability of each outcome, or the probability of one of those outcomes. Say the heads. The probability you get a heads, well, maybe that's always going to be 50%. But if I flip that coin 5 times, that's the blue lines here, that would say that, well, there is a chance that I get a heads 0 times. Right? I'd get 5 tails in a row. There's also a chance I'd get 5 heads in a row and 0 tails, right, out of 5 coin flips. But those 2 things are very unlikely. It's more likely that I'd get at least, say, like 1 head and 4 tails, or maybe 1 tail, 4 heads, okay? But it's most likely that I'd get 3 and 2, right? Because it's equally likely, I'd expect that I'd probably get about half of them heads, half tails, which out of 5 coin flips means about a 3 or 2 split, or 2-3 split, okay? So that's this blue line. That's what the blue bars here are representing. You're most likely to get values in the middle of the range, but it's possible that you can get values as high as 0 or 5 out of 5 coin flips, right? You can get as few as 0 heads or as many as 5 heads if you flip that coin 5 times. If, however, the red line, if, however, you flip that coin 20 times, right, now there's 20 possible values, right? However, the likelihood that you flip a coin 20 times and get 0 heads, and it's tails 20 times in a row, is extremely unlikely. It's almost 0 probability, pretty much. In fact, what you'd expect is 10 heads, right? Half heads, half tails, right? So you'd expect about 10 heads to be the most likely outcome, but you could expect maybe 9 or 11 are pretty close to the same likelihood, right? Maybe one of those comes out a different way than you might expect. And maybe it's an 8 and 3, or I'm sorry, whatever, 20 experiments. Maybe it's 8 and 12, or 12 and 8, and so forth. So you can see the red bars here representing the likelihood of how many heads you flipped out of 20 coin flips, okay? The green line now is even if you did more experiments. Let's say you did 50 coin flips. The most likely outcome is you'd get 25 heads, 25 tails, right? But you might get 24, 26, 26, 24, and so forth. What you'll see is the binomial distribution, the more experiments you're doing, the higher the N, the smoother the outcome, the smoother the distribution becomes. In fact, the more normal it looks. It looks like the normal distribution, okay? Again, we can go through reams of textbooks about the math of why that works out, but we won't. we're not interested in that. This is just one kind of distribution. Okay, if you had a Bernoulli distribution that is 2 outcomes, and you just repeated that over and over n times, the binomial distribution says out of those n times, here's the expected number of zeros or the expected number of ones that you'd see. Okay, so that's Bernoulli and binomial distributions. Okay, mainly, more often than not, I'd say you'll be looking at using the normal distribution, maybe a triangle distribution, maybe a uniform distribution. Those first 3. Special cases will come up when you have something with 2 and only 2 outcomes, like flipping coins or something like that, where you use a Bernoulli or a binomial distribution to represent those. In Excel, in an analytic solver platform, they have the ability to represent all of these distributions and dozens more. Okay, so there's many more random variable distributions than just these. We won't concern ourselves with them for this class. Okay, if you ever wanted to take this material and apply it at a job site, you might consider whether or not a different distribution would be appropriate when you're doing simulations. But for brevity's sake, for this class, we'll just focus on mainly the first 3 and possibly these last 2 distribution types. Okay. All right, so let's do another example using simulation. So here, this is a little less complex of an example than we did first. So we were looking at sales numbers for 6 months and costs that we'd have to take and loans we might have to take out to make up for differences and so forth. Here we're just going to consider something very simple, but it's a very contrived example in that we're going to use multiple different distribution types. Okay, so let's say we're an electronics firm and we make battery rechargers for cell phones. So basically there's a price at which we can sell these things, a cost at which we have to pay to build the unit, the product, and there's a quantity for how many we think we can sell, and then a fixed cost, right, to pay our workforce and electricity for the building and rent and all those other kinds of things. So our unit price, that is the amount we can sell each unit for, we'll assume is a triangle distribution. That is, we have a pretty good idea there's a minimum price we'd ever charge and a maximum we'd ever charge. And some value in between there is the most likely or expected value. The mean, you might call it the mean, you might call it expected, you might call it most likely value. Okay, so the minimum is $18.95. Most likely will be at about $24.95, but we might set the price as high as $26.95. Okay, so that's the random distribution of the unit price. Unit cost we'll assume is a uniform distribution with a minimum $12 and a maximum $15. Okay, so we don't know if it'll be $12. We don't know if it'll be $15. We know it's somewhere in that range, but any value in that range is as likely as any other. That is, whatever drives costs, buying materials, whatever it is, we don't have control over it necessarily, but we have a known range at which we'll buy those materials. But since we don't know anything else, we'll assume it's uniformly distributed because maybe we have no idea what a most likely value would be. The quantity sold will be a computation. That is, we'll sell 10,000 units, sort of base case, minus 250 times every dollar unit price. That is, the higher we set the price, the fewer we sell. Okay, that is, people, fewer people will buy the product, the higher the cost goes. The lower the cost goes, the more people might buy it. Okay, so 10,000 minus 250 times the unit price, plus we're going to add a random term given by a normal distribution with mean 0, standard deviation 10. That is, there's some amount of fluctuation in the market of how many battery rechargers we can sell that we just can't account for. That is, we don't know what makes some people buy on a certain day but not another. So we'll represent that sort of unknown uncertainty as a normal distribution with mean 0, standard deviation 10. So we might sell 10 more units, 10 less units, we're not sure. So that's that. That's why normal distribution like this is good for those kinds of random terms where it's not going to, you can't exactly predict it. There's some randomness out there, so you have no idea, whether it'll be more or less, but you have an idea at least of a range of how random it could be. And then finally, the fixed costs will be normally distributed with a mean of 30,000 and a standard deviation of 5,000. So maybe the fixed costs represent rent, and rent can go up or down a given month depending on the real estate market, or maybe it's electricity we have to pay for, and the electrical company sets rates every month, and they can be different. So we don't know what they're going to be, and we don't really have an equation to predict them, so we'll just represent them with this random or randomly chosen value that's normally distributed. Okay. All right, so let's take these values and start putting them in to an Excel sheet. All right, so we'll say we had our unit price, unit cost, our quantity, and our fixed costs. And for some of those we had a min and a max. For some of those we had an expected value, and for some of them we have a standard deviation. Okay. So for the unit price, if you remember, we had a triangle distribution, I believe, and the minimum was $18.95, the maximum $26, and the expected value, that is the most likely value, was $24.95. Okay. Go back and check and make sure that's right. 18, 24, and 26. Looks good. Unit cost uniformly distributed between 12 and 15. $12 and $15. Quantity, well, the parameters for the random part of the quantity was there was a random term with a 0 mean and $10 standard, or 10 unit standard deviation. Okay, so we'll represent that here. Excuse me. Fixed cost had a $30,000 mean and a $5,000 standard deviation. Okay, so let me format the cells that need formatting. So these are just copying in the model parameters, and we'll put this down here. Base quantity was 10,000. Quantity per price was negative 250. So base quantity of 10,000, but for every dollar increase in price, or every dollar of price, we sold 250 less units. Okay, so now we can do our calculations. So first we need to calculate, well, let's see. First we need to compute our random numbers. So we'll call unit price. So that's going to be a distribution. We said our price was a triangle distribution. So here I'll set triangular. So you'll see it brings up a chart, looks very triangular, and the parameters over here to the right, there's a minimum, a maximum, and a likely value in between. So the minimum was here in C2, the likely value was in E2, and the maximum value was in D2. Okay. So that's what that triangular distribution would look like. So a minimum of 18.95, a maximum of 26.95, and a most likely value here of about 24.95. Okay. So again, during our simulation, we're going to compute a new value here taken from that distribution. That is, we'll randomly select a value according to that distribution for this cell. In this case, it's so far randomly selected $25.08. Now that we know price, we can calculate quantity. So quantity was the base quantity plus this quantity per price factor times unit price, okay, plus a normally distributed random term. So I'm just going to show you how you can literally just enter the equation in here. So PSI normal, and the first parameter is the mean value, expected value. The second parameter is the standard deviation. Okay, so let's just see that equation one more time. So literally we've computed quantity as base 10,000 minus 250 times the unit price that we've simulated. Okay, so the unit price randomly chosen here, plus a normally distributed random value with mean 0 and standard deviation 10. Okay. Quantity is not currency, but it is a number. Okay. So now we can compute unit cost. Well, unit cost was a simple uniform distribution. So again, in the distributions under common, there's an option for uniform, where you can set the lower minimum value and you can set the upper maximum value. Okay. Format that as a currency. And then we have our fixed cost, which is again normally distributed. So I'm just going to type it in instead of clicking the buttons. Either way, if you know the names of the functions, PSI normal, PSI uniform, PSI triangular, you can just enter them in. Okay. All right. So that gets us some of our base, calculations. Now we actually need to compute something like revenue, which is the unit price times the quantity. So how many we sell them for times how many we sell.
Sorry, I can't
Okay.
keep up.
Can't keep. Okay, that's all right. What cell do you need to see?
How'd you get those equations? That one.
So
Did you just drag it down or something?
this one I entered in. So let me zero out that cell. I'll show you how I enter. So the fixed cost, we want to simulate a fixed cost with these normally distributed parameters. So we think fixed cost will be 30,000 plus or minus a standard deviation of 5,000. So one way you can do that, if I'm going to put that equation here, is to use the distributions button in Excel on the Analytics Solver platform tab, and under the common distributions. So again, Analytics Solver platform has lots of distributions you can use. Mainly we'll be working under common, where you'll find normal, triangular, and uniform. So in this case we want the normal distribution. So it brings up a chart or graph that represents that. By default, the mean is 0, the standard deviation is 1. Well, we want to change this mean to be, I have to move this out of the way. I'm going to change the mean to be cell E5, that is 30,000. And we want to change the standard deviation to be cell F5, okay, which is the standard deviation amount, right? The parameter we got from the problem description. So once I've entered those two things, I can click Save, and you'll see merely the function it put in here is just equals PSI normal, and the two parameters to that function are E5 and F5, the mean and then the standard deviation. So you can just type this in if it's faster. Okay. So unit cost was uniformly distributed. So there's two parameters to a uniform distribution, the minimum and the maximum. So you can literally just enter in equals PSI uniform, and then in parentheses your minimum, comma, your maximum. So those are what I had in cell C3 and D3. Quantity maybe is the most complex one because it has both a normally distributed term, so PSI normal with a mean of 0 and a standard deviation of 10, but it also had a sort of computed portion, which is simply the base quantity, that 10,000, and I did plus because my value here is negative, so really it's minus 250 times the unit price, which is cell C11. Okay. So those 4 parameters there are basically the in some ways you can say computation, but really it's just the generation of a value taken from distributions of random values governed by these parameters we put in up here. Okay, so the price is normally the price was triangle distribution, the cost was a uniform distribution, quantity was something computed based on price plus a normally distributed random term, and then the fixed costs were normally distributed. Okay, so once I had those 4 things computed, I can compute overall revenue, which is the unit price times the quantity. I can also compute total costs, which are fixed costs plus the unit cost times the quantity. So for the 4,000 we sell, we have to pay, we think, something like $12.81 plus just the fixed costs. Okay, which, by the way, I never made look like a currency. Go. And now we can compute profit as revenue minus total costs. Okay. Again, I like to highlight or fill that cell with something like green, just so you can see that that's what we're interested in visually. And before we can do our simulation, we have to tell the analytic solver platform that cell C17 here is the cell we want to see graphically represented. That is, we want to see the distribution of what value gets computed in cell C17 given different randomly generated values for, say, price and quantities and costs and so forth. So we select cell C17, the profit. We click the results button, output, and say that the output, the result output that we're interested in is in this cell that we've selected, C17, which adds to that cell the PSI output function. Okay. All right. So now that we've done that, you can either click the simulate button and tell it to simulate once, or if it's quicker for you, you can double click the output cell that you've selected or that you've designated. And if you double click it and it hasn't run simulations yet, it'll ask you if you want to. You can say yes. And again, by default, what it's done is it's it's generated 1,000 sets of values randomly picked for prices and costs and quantities and all that, and then graphically depicted the profit that gets computed from that. So you can see the expected average profit is about $10,000, $10,712. Okay. That's how much profit we think as an electronics company we're going to make given these various parameters for our distributions of uncertain values. Okay. At minimum, actually the minimum here negative, meaning we think we might actually lose money. That is, costs outweigh revenues up to $13,000 worth. Okay, but at maximum we could make up to $30,000 of profit. Okay, so there's a chance that we'll lose money, right? According to these parameters, this model, there's a chance that the costs will be high and the price and quantity will be low, such that we don't make enough money to cover our costs, right? We lose money. We might ask the question, what's the probability of losing money? That is, what's the probability that our profit is less than $0? So to answer that question, we can come to the chart and change this first number up here to be 0, which will tell us the percent likelihood you have less than 0 versus the percent likelihood you have anything up here between these two ranges that's above 0. So the likelihood that we have a profit less than 0 is 6.6%. There's a 6.6% chance we lose money as a company, that we owe more than we make, okay? And our profit is negative, which basically means there's what, a 93.4% chance that we make money. So more likely, obviously, that we're going to make money than anything. We might also ask the question of, what's the likelihood that we make more than $15,000? So I can change one of these range values here again. So the likelihood we make more than $15,000 in profit would be 27.8%. That is, roughly there's a 1 in 4 chance that we'll make more than $15,000 of profit. But there's also a 6% chance, 6.6% chance we'll lose money, okay? So forth. All right. Are there still questions? Do you need to see some of the equations again?
Yeah.
Okay. What equations do you need to see?
That last one, I couldn't see what you were typing.
The profit?
Yeah.
Okay. Profit is just the revenue we computed minus the total costs. Plus, it adds in this PSI output function, which is what tells Analytics Solver Platform that this is the value. The value computed here is the value we want charted, and we want to see the distribution of. Okay. That PSI output doesn't really change the number. It just designates that the equation number computed here otherwise is the one we care about. So revenues were unit price times quantity, so the amount we sell each unit for times the number we sell. Okay.
So why are all our answers so different?
So the question is, why does everybody get a different answer? Because everybody randomly selected different values, right? So my computer at this point has randomly determined the unit price to be $24.39 because it's picked that value from this triangular distribution. Your computer might have picked a different value. In fact, the likelihood is everybody picked a different value, right? Because everybody randomly chose some value in this range with this kind of a likelihood. So forth. For quantity, costs, fixed cost, unit cost, everybody's computer's picking a value according to some random distribution. The likelihood is we're all picking different values. Now when we do a simulation, so again I'm going to double click the output and show you. When we do a simulation, we will all technically get a different looking distribution. That is, the likelihood that we all generated 1,000 simulations that led to a mean, minimum, maximum that are all the same is pretty low. However, if you get a value that's wildly different as a mean than mine, that's a pretty good indication that's either you've done something wrong or 1,000 simulations isn't enough. That doesn't represent enough tries to get something reasonable. That is, there's still a lot of uncertainty. Now maybe you got $10,600 or maybe you got as high as $11,000. That's possible. If you got something like a mean of $50,000, again, that's wildly different. Maybe there's something wrong, okay? Or maybe there's just that much uncertainty. Maybe the parameters have such a wide range that even with your 1,000 simulations and my 1,000 simulations, we never selected values that were equivalent or close to one another. That also means when you, especially in your assignment, when you answer the question like, what's the probability of a loss? So again, if I computed probability of a $0 profit, this time, if you remember last time it was 6.6%, this time it's 6.5. So theoretically, I might answer a slightly different number than you, even though we computed the exact same model, exact same parameters. Now, it'll be close to one another. Everybody's going to get 6 point something, most likely. But theoretically, everybody could get a slightly different number because their computers randomly selected slightly different values for the 1,000 simulations. The 1,000 times it did what it did, it picked slightly different values, leading to an overall output distribution that looks slightly different. Okay, so don't ever look at somebody else's work in a simulation study and try to compare straight up equal your results with theirs. Unless your computers, randomly selected all the same things, you won't get that. Does that answer the question? Okay, good. Any other questions about simulations? How they work? So this example was instructive merely in the case that it basically demonstrated how we can use triangle distributions, uniform distributions, normal distributions, all within the same model. Okay, so again, if I double click on any of these cells that have these distributions defined in them, it'll bring up and show me here's what that distribution looks like. Okay, so here's what unit price. Here's what a randomly selected unit price would look like in terms of how likely each value is. Here's even quantity. You could see the normal distribution part of that is a normal distribution with mean 0, standard deviation 10. Okay, so that's what that looks like visually. Unit cost was uniformly distributed. It's a pretty boring chart, but that's what a uniform distribution looks like, right? It's just a big box because every value is as likely as every other value within the range. And then fixed costs were normally distributed, so they look like this. And our output, as a result, the profit computed, having to rerun simulations, but the output profit computed looks like this. So obviously it's not normally distributed because there's aspects of this problem which are not normally distributed. There's aspects that are uniform, there's aspects that are triangularly distributed. But it's obviously not triangle or uniform either because it's a mixture of all those things. There's, I think, 2 normal distributions, a triangle distribution, and a uniform distribution combined in different ways, right, through different equations, that comes out making a distribution that looks something like this. Okay, from which we can ask or answer various questions about likely values or how likely certain range of values are, how likely losses or gains are, and so forth. And again, we can use this sensitivity tab to sort of tell us which parts of the model affect profit more than any other, how much more they affect profit than other cells. So for example, C14, which is the fixed costs, C14 fixed costs affect profit more than any other individual cell. Okay. So the random part of fixed costs, that is because they're normally distributed, they can take on different values. The range and the effect that range of random values has on profit is a greater effect than any other individual cell. And it's negative, meaning the higher fixed cost, the lower the profit. Makes sense. Obviously that's what you expect. But now we know if we could somehow get our fixed costs under more control, that is, we could either be more certain about their value, or we could increase or decrease their value by some method, that alone might help control or help make our profit more certain than any other individual thing we could do. Followed by the second most likely thing, or second most sensitive parameter, is C13, the unit cost. Okay, so it's interesting that the unit cost affects profit more than the unit price. Okay, unit price is the third most likely, and they're not far off, 0.42 and 0.53 in terms of their effect. So they're not far off, but technically unit cost drags down profit more than unit price brings it up. Okay, according to the simulation, according to the numbers, changes to unit cost affect profit more on average than changes to unit price. Okay. Now, part of the reason that is, okay, just to give you a little bit of an explanation, part of the reason that is likely because unit cost is uniformly distributed, so it really does take on a wide range of values, versus unit price, which is a triangle distribution, which tends to hover closer to the expected value. So more often than not, it's close to the expected value, even though it might possibly go as far as the min and max. Whereas the uniform distribution, just every value is equally likely. It may be the min one time, the average between the two, the next, and the max after that. It'll always jump around. That's probably why unit cost has a higher effect than unit price, is because its distribution lends it to being more variable and being a wider range of values for any given simulation. And so, okay, so that's sensitivity. We can answer the question here of basically what affects our output. That is, what affects profit? What is the driving force behind profit? And the answer really is that fixed costs, unit costs, affect profit much more than other things. Really, fixed costs, unit costs, and unit price affect profit. Everything beyond that has a very small, little effect on profit. That is, cell C12, the quantity, right, has little effect on profit. That the uncertainty of cell C12, that is, the part of C12 that's normally distributed, doesn't really affect profit that much. Affects it very little. Because that normally distributed part is a very small range of values. That is, it's only 0 plus or minus 10 or 20 on average that it affects, that quantity changes. And that effect on profit is overall very small. Okay. Sensitivity, frequency of profits. Any other questions about simulations? Okay. Before we end our talk about simulations, I want to take just one moment and let's look at assignment 7, which should be posted to Blackboard now, just to make sure you understand sort of what we're going to do. So, literally, okay, this should be easy, but exercise number 1, okay, is the same problem we just did. Same numbers, anyway, for the problem we just did. The questions that I'm asking are a little bit different, okay? So I didn't necessarily ask all of these questions when we did the problem just now, but you'll have to figure out how to answer these questions. So maximum loss, that is, what's the most negative profit possible in the simulation, or maximum profit, or probability of a certain profit minimum, that is, a profit of 100,000 or more, and so forth. So you're going to have to figure out from that frequency chart, that distribution, or sensitivity or sensitivity chart, and so forth, how to answer these questions about the situation or the problem described up here with these different uncertain parameters. Okay. exercise number 2, something somewhat similar. Exercise number 2, the key is, so what the problem is you're going to be a door-to-door salesman. You're going to go to 100 houses, knock on the door, try to sell them something. We have uncertainty in whether or not somebody's home. If somebody's home, whether or not they're going to buy what you're selling, and if they're going to buy, uncertainty about how much money they'll spend. That is, how much they'll end up buying. Okay, so there's parameters described here, and the distributions I want you to use for those described here. Essentially, several of those parameters, like whether or not somebody's home, that's a Bernoulli distribution. That is, there's only 2 possibilities. There's nobody home, or there is somebody home, right? And so when I say that there's an 80% chance or an 80% likelihood that somebody is home, that's a Bernoulli distribution where one of the outcomes is 80% likely and the other is 20% likely, right? Because that's the only possibilities. When there is somebody home, I say there's a 65% chance that the person is female, meaning there's a 35% chance that the person is home is male. So 80% of the time somebody's there, 65% of those 80% of times it's a female, 35% of the 80% it's a male, okay, and so forth. So females buy at a certain rate. We're going to assume males buy at a certain rate in terms of whether they buy and how much they spend. So in the end, what you need to do for this problem is you're going to create a model, okay, that has 100 rows. Let's say 100 experiments. Like if you were flipping a coin, there's 100 outcomes, right? So 100 times you're going to compute the probability that somebody's home at house number 1, house number 2, house number 3. 100 houses, okay? Probability somebody's home. If somebody is home, you're then going to compute the probability that they are a female versus a male, okay? Given that they're, say, a female, you're going to compute the probability that they actually buy something, whatever you're selling, and how much they're going to buy, how much money they'll spend. If the person home is a male, there's a different distribution for whether or not they buy and how much they spend, okay? So in the end, essentially what you're going to have is basically 100 rows, 100 sets of randomly selected values, okay, for whether or not somebody's there, who it is, whether they buy, how much they spend. And what we compute at the end is how much did we sell? How much money did we take in? That is, how many dollars worth of product did we sell? Obviously, the amount we sell is going to be distributed, right? Some range of values based on all these other uncertain parameters. Okay, so then you're going to have to answer these questions about expected values and maybe minimum values, maximum values, probabilities, and so forth. Okay, so just want to make sure that's clear. So we're first talking about 100 different simulation or 100 different cases, homes. Each home, right, may or may not have somebody there, may or may not have somebody who will buy something, and so forth. You're going to sum up how much money you sell across all those 100 homes. Okay. Some of these parameters or some of these uncertain parameters are Bernoulli parameters. That is, they're 2 outcomes. Some of them are, I think, normally distributed. I said. Some of them, well, that's it. So Bernoulli, so whether or not somebody's home, whether or not the person home's female or male, whether or not they buy or don't buy, all of those things are Bernoulli distributions. Okay, only 2 possible outcomes. How much they spend is normally distributed, we'll assume. Okay. All right. Any questions about assignment 7? So hopefully exercise 1 is easy enough. You more or less have the model that I built tonight recorded for you. Exercise 2 will get a little more tricky, but definitely doable. Okay, you can do it. Again, I would do it the same way, or roughly the same way I did this exercise 1 tonight. I'd first create the Excel sheet and just put in the values of all these distributions so you can refer to them, okay? And then I would just go through and create one row for house number 1 and compute, is somebody there, okay? And then compute, given somebody is or isn't, who is it, male or female? Given that, what's the likelihood that they actually buy from me? Okay, so if nobody's home, it doesn't matter if male, female, nobody's there, they're not buying, right? Nobody's home, nothing's sold. If somebody is home, they might buy. If they do buy, how much did they buy, right? So start with creating house number 1 for that, and then basically just copy that 100 times for 100 different houses. What you'll see is across those 100 houses, right, it's randomly selecting whether or not somebody's home at each house, and then based on your equations, it's computing whether or not it's male or female and whether they buy and how much they spend. So in the end, what you'll see is you're going to be selling, you're actually going to get money from a small percentage of these 100 homes, okay? Because sometimes nobody's there. Sometimes somebody's there, but they don't want to buy, right? So some fraction of the homes you'll actually have sold product to, some amount, dollar. You're going to sum that dollar amount up of all those sales, and that's going to be the profit or the output that we want to measure. Okay, that's all I had. So that concludes Tools of Operations Research. Now, we did not cover everything possible, okay? There's plenty of topics in the textbook and beyond that involve tools of operations research that we did not cover. But basically, we've covered most of the basics in 3 or 4 different fields, okay? And this has concluded simulation studies. Now, simulation did not involve optimization, okay? So we didn't say simulate or pick these random values and then optimize for some maximum profit or minimum cost or something. There is a place for doing something like that. In fact, there's a chapter in the textbook that talks about it. We're not going to cover it because we don't have time, but you can do a combination of simulation with uncertain random parameters plus optimization, where you try to find an optimal decision variable or variables, values for those to maximize or minimize some objective. Okay, so just have that in your mind, not for this class, not for the final, but in general, that just because we've talked about optimization and simulation as 2 independent things, there's ways you can combine them. Okay, and there's ways you can combine lots of the other topics we've talked about in interesting ways. And there's techniques we didn't cover that involve either data mining or forecasting or optimization, or there's other topics like decision trees and other things that the book covers that we just simply didn't have time for. All right, well, that concludes lecture number 7.